Okay, welcome period 8. You are watching this for various reasons. Period 7, say hello.
Hello.
Woo! Okay. Good. So, like I was just saying a minute ago, before I hit the record button, things are bad. All of mathematics rests on set theory. Set theory is ubiquitous in the rigorous mathematics, which has come to dominate the end of the 19th century. Set theory is inconsistent, and therefore our entire mathematical structure, all of our theorems, all of our justifications for thinking all our theorems are true, the entire structure has just collapsed and somehow needs to be fixed. It's unclear what to do and how to do it. All right, here are two sort of unrelated but tangentially related other things that are going on around the same time period, which are also leading mathematicians to start disagreeing with each other more than they're agreeing with each other. All right, this subject which I'm about to talk about right now is something which deserves hours, and we're going to give it 25 minutes. Are you ready? All right, 25. There's this thing called the Axiom of choice. Has anyone heard of this before? Yes. Like 3 people. Perfect. Anson's G-chatting me as I'm...
Oh yeah, I sent you a meme. It's like a Photoshop, it's like a
pretty good meme.
Yeah, is it funny?
It's a pretty good meme, yeah.
What
is it?
It's quite good, actually.
Yeah,
good. We'll put it up later at the end. Okay, good. Alright, so here we are. It's 1900. We're at the Paris Conference of the International Congress of Mathematicians. And Hilbert, we're going to have an entire presentation about this, announces to the crowd what he thinks are the most important problems to be solved in the 20th century. And the very first problem is Cantor's continuum hypothesis. And if you will recall, what is Cantor's continuum hypothesis? Let's do this. It is the hypothesis that, can someone keep like jumping up and making sure like everything I do is in frame? Guys, we're done. It is the hypothesis that there exists no set whose size is in between the size of the naturals and the size of the reals. So the simplest way of saying it, which is the way we first did it, is like this. And here we wrote no, right? There is no set whose size is in between that. But then, if you're willing to get all the alphas involved, the size of the naturals is alpha naught, the size of the reals is 2 to the alpha naught. And so the question becomes, is there a number in between alpha naught and 2 to the alpha naught? And then, if you recall on Ordinals Day, the very, very end, we defined the next cardinal, aleph 1, to be equal to omega 1, the first uncountable ordinal, which is guaranteed by the ordinal construction to be like sort of like the smallest set which is uncountable. And so an alternative formulation of the continuum hypothesis is that is that aleph 1 is 2 to the aleph naught. Okay, so these are just a couple ways of saying the continuum hypothesis. This is one of Cantor's things that he tried really hard to prove, and he couldn't do it. So all right, good. Well, Hilbert suggests that this thing called the well... Can I just leave you to do all the focusing and stuff and framing and everything?
I'm sure.
And then I can just not worry about it? No, not focusing, just like framing. Just like, that's perfect. Okay, good. Cantor has been using this theorem, this thing called the well-ordering theorem, freely throughout the end of the 19th century. And only towards the end does he start to think, I should maybe try to prove this. Some people find it strange, many people find it totally intuitive, others find it unintuitive, and people try to prove it. Okay, what is the well-ordering theorem? It is different from the well-ordering principle, something which we definitely talked about in discrete if you took discrete, and even if you didn't take discrete, I think we discussed the well-ordering principle, I think, in this class. It's the principle that every non-empty set of natural numbers has a least element. And under our normal way of ordering the natural numbers, this is of course true. Given any set of natural numbers, you can just pick the smallest one. Yeah, this clicker stopped working. Great. All right.
Try rotating the batteries.
Oh man. Woo! Excellent video. Someone tell a joke during this pause.
Talk about Anson's meme.
Hold on.
Someone could like control the computer.
What did one wall say to the other?
I don't
Let's meet
know.
at the corner.
What I really need is a no, don't pull to me.
Or what did the ocean say to the beach? Nothing, it just
Hold on.
waves.
Oh, wait, now I regret doing this.
One of them orders half of a beer. The
That's
next
one
orders a quarter of a beer. The next orders an eighth of a beer. The bartender says stop and pours one beer and says know your limits.
Good. That, yes, solved the problem. It was the old battery, the battery thing. Good. Woo! Okay, we're back. Okay, great. The natural numbers have an ordering, so there's always a least natural number. That's fine. All right, so we say, this is kind of review actually, because we talked about this within the ordinals presentation, that a set is well ordered if it has a strict total order and there is always, every subset has a least element. And the total ordering is just is a relation for which for any two numbers, one is less than the other, and it's transitive and whatever. Okay. So here's just some basic examples of orderings. The natural numbers are totally ordered, and they are all, that total ordering is also a well ordering, because given any subset of the naturals, there's always a least element. The integers are totally ordered, but that total ordering is not a well ordering, because it's simply not true that if you take a subset of the integers, that there's always a least element. For example, take all the negatives, there's no least element. Good? You could order the natural numbers differently and start counting them like 0, -1, 1, -2, and then now the set is well ordered. So you can come up, sometimes a set has a standard ordering, and then there's like some new ordering under which it is well ordered. The reals are totally ordered as well, but certainly that normal ordering on the real numbers is not a well ordering, because again you take all the negatives. The well ordering theorem says that every set can be well ordered, even the reals. All right. This is a kind of a do you have any thoughts on this for just a second? What this means is the well-ordering theorem, as applied to the real numbers, says that if you take the real numbers, under their standard ordering, they are certainly not well-ordered, but it is possible to well-order them. In other words, it is possible to put them in some kind of order so that in any set of real numbers, there's always at least one. Let's talk, yeah, Justin.
Well, we did this for the rationals, right? Were you able to do like a zigzag?
We were able to do this with the rationals. It's true, yes. If you consider the zigzag to be putting the rationals in order, which it is, then that is not the standard ordering, but that certainly is a way of ordering the rationals. But make a comment on that, yeah.
So that let us get the rationals in a countable way, right?
Yeah.
And the reals accountable. So that seems counterintuitive.
Yeah, the fact that the rationals can be well ordered is not so surprising because they're countable, is what he just says, right? So there is some way of listing them, and that listing is an ordering, but the real numbers are just not countable, definitely. And so if the set is not countable, how could there possibly be like a first one, a second one, a third one, etc.? Yeah, Anton.
Wait, what? You don't need the first one, second one, third one to have a well ordering, right? Why can't it just be like the ordering is closer to 0 is lower, and like negatives are lower than positives. Tie when you break the tie, negatives makes it positive. Then any subset of the reals will have a smallest element, namely the lowest magnitude element.
But like some sets, like for example, take all the reals in the open interval 0, 1.
That's true.
That's kind of why this is that's why this is intuitively sort of false, right? Or it's intuitively really, really hard to imagine. Take all the reals on the open interval 0, 1. There is no obvious least element, at least on the standard ordering. Cantor thought that he thought it was obvious. He considered it not just true, but obvious that every set can be well ordered in some way. Now he could, yeah.
For a well ordering of the reals. How
Yeah.
about like closest to an integer, and then you like break ties in normal integer ordering or something like that.
But you have the same problem, right? Because there's no closest number to like 1. There's no closest real number to 1. Yeah, we have a problem. There is no. Okay, you can try for a long time. You are not going to be able to just on the spot come up with some well ordering of the real numbers. And this theorem struck some people as, or this proposition struck some people as just sort of obviously false. And Cantor somehow thinks it's obviously true. And it actually comes from Cantor's conception of sets, which is that they come inherently structured. He believes in some kind of weird way, Cantor, that every set was made in some kind of order, like by God or something. And that the ordinals sort of explain the order in which that set was made. It was sort of built out of smaller things. And the way one way you might try to prove the well ordering theorem is to put all the real numbers in order. Okay, so take all the real numbers. Let's put them in order. Ready? Just pick one.
5.
Pi.
She said, I heard pi. Okay, let pi be the first real number. Okay, pick another one. 2. Let's make that the second real number. We could just keep on doing this. Arbitrarily picking real numbers and calling that the next real number. What's the problem with this? We're not going to be able to enumerate all of them because no matter how long we pick, we've only picked a countable number of them, right? So basically what we do is we just keep on going. We don't stop after doing this a countable number of times. We pick like up through all the ordinals. And we just keep on picking until we reach an ordinal that's larger than the set of real numbers is, which we have to hit eventually. This is essentially the proof. I'm kind of skipping around in this thing. All right. So this guy, Ernst Zermelo, German guy, in 1902, he tries to prove the continuum hypothesis. And in doing these proofs, he finds these very, very, very low-level, extremely abstract proofs. He realizes that he keeps using this principle. And he is the first one, we consider him to be the discoverer of the axiom of choice, because he's the first one to sort of articulate this principle and to say that he is applying it and to just sort of make a note of this. And he proves the well ordering theorem. And he proves it from the axiom of choice. Okay, what is the axiom of choice? All right, we're all going to leave this room today not really understanding this, so just be okay with that, first of all. But the axiom of choice, broadly speaking, says that you may kind of pick a number whenever you want. You can, at any point, from any set, you can pick one. You can pick an element from that set. Okay, more specifically, take a collection of non-empty sets. Say you have a whole bunch of sets. That's called a collection of sets. The axiom of choice says, loosely speaking, that you may, for each of those sets, pick from that set an element. All right, when you say it like that, it sounds kind of innocent. Why would I not be able to pick number out of a set? Okay, great. So here's an example. This picking, this ability to pick, is called a choice function. Okay, so for example, these are some silly examples. So let S be a set of chickens. Pick the fattest one. Okay, let S be a subset of the naturals. Pick the least number, etc., etc., etc. Okay, but what if instead you have now one possible collection of sets is the set of all subsets of the reals? recall that to prove the well-ordering theorem as applied to the real numbers, I would have to, via any subset of the real numbers, there has to be a least element. And in order to well order the real numbers, what I really need to do is pick a first real number, a second real number, a third real number, a fourth real number, etc. And I can do that, but the conversation kind of goes something like this, right? It's like, so suppose that, yeah, here it is. Let's just kind of, maybe we should just take this presentation seriously in order. Okay, so here we go. The axiom of choice in action. This is a theorem. What does it say? If a set A is infinite, then there exists a one-to-one injection, or an injection from the natural numbers to the set. Okay, so take an infinite set, say the reals.
Main office, can I help you?
No, I didn't hit the button, sorry.
Okay.
So take the reals, for example. There are an infinite number of reals. Do you believe that there is an injection from the naturals to the reals?
Yes.
Surely, right? Okay, how can I show that there is an injection from the naturals to the reals? The naturals are are a subset of the reals. And so, what Olivia is recommending we do is to match the natural number 0 to the real number 0, the natural number 1 to the real number 1, etc. Right? And that does it. Congratulations. Okay, but now, more abstractly, Olivia, prove to me that an arbitrary set A, which is infinite, has a one-to-one injection from the natural numbers to that set. You see the subtle difference now, right? Now, instead of, Olivia just gave us on the spot a one-to-one function from the naturals to the reals. But now I want a one-to-one function from the naturals to an arbitrary infinite set. All right, what are you tempted to say at this point?
Choose an element from the set.
Exactly. Yeah, Jonah says, I'm tempted to say, the Olivia-Jonah combined answer, it's tempting to say, okay, first match 0 to like a number from that set A. But which number? Just any number. Well, which one? Just any one. Just pick one. Okay, so then you pick one. Suppose you're allowed to do that. And then, what should we match 1 to? Another number. Which one? Just pick one. Which one? Just any one. Just pick one, right? Do you see what's going on here? I am, quote-unquote, constructing an injection from the naturals to this arbitrary set A. But this, quote-unquote, construction is somehow dependent on my ability to arbitrarily just like pick an element from an infinite set. And some mathematicians did proofs this way, in which they gave themselves this sort of power to just pick an arbitrary element from a set. And other people read these very same proofs and said, what are you doing? This is not math. This is like, you're just telling me to pick an element. Which element? Just any one you want. Well, which one? The very nature of what counts as a mathematical construction is under discussion. And in defense of this concept, Zermelo proposes this thing called the axiom of choice. The axiom of choice says we may pick essentially an arbitrary element from a set. Or more specifically, if you have a collection of sets, we may define a function which from each subset extracts a particular element, but without telling you which element we're picking. Is everyone kind of with me? This is actually like a very high level and pretty decent. I could almost just stop this presentation right now and just call it a day. This is the axiom of choice. Zermelo, to his credit, realizes that he can't prove this property, but thinks of it as so obviously true that he just calls it an axiom, and he says that this axiom is clearly true and that we must have this axiom to do mathematics. Woo! And this is probably what's going on here, right? This is the proof of the thing we just talked about. So A is infinite, so here's what you do. Base case, let 0 go to some element in A. And then, let's see, what are we doing? And then we take that one out, basically, right? And then we just like pick another one from the rest, right? Yeah, it's exactly what we said. All right, so cool. This is an example, this proof we just gave that we talked out, of making an injection from the naturals to an arbitrary infinite set. of a non-constructive mathematic, well, actually, it's not necessary, well, let's talk about the difference between constructive and non-constructive. A constructive proof is a proof which tells you, okay, this is hard to explain. It's a proof which sort of makes the object under discussion. So what the hell is going on here? Here is the theorem. The theorem is that an irrational number, prove that there exists an irrational number taken to an irrational power which could be rational. In other words, wake up, Mark. There exists a pair of irrational. I used to do this in functions. That there exists a pair of irrational numbers that so x and y are both irrational, yet x to the y can be rational. Okay, do you believe it?
Yes.
All right, it says yes. I don't know if I believe it yet. Let's see a proof. Okay, here comes the proof. Ready? The proof is the proof on the right I want to talk about first. It's very kind of disappointing. Here's what it says. Okay, it says take root 2. Well, root 2 is irrational, provably. And so let's raise a to the power of d. Well, the goal was to show that it's possible to have an irrational to an irrational which is rational. So first of all, what is it?
I think this is
It's a
wrong.
typo.
I think it's a typo. If it's rational, we're done, right? Because then, okay, so if it's rational, we're done. So that's good. But if it's irrational, so now so there are two options, right? Root 2 to the root 2 is rational, in which case we finished. On the other hand, case 2 is that root 2 to the root 2 is irrational. Yeah? Okay, but if it's irrational, then you just pull this trick where you raise the whole thing to the root 2. And then root 2 to the root 2 to the root 2 is by exponent rules root 2 to the root 2 times root 2, which is root 2 squared, which is root 2 times root 2, which is 2, which is rational. Woo! In other words, if root 2 to the root 2 is rational, we're done. And if it's irrational, we have also produced a pair of numbers which are both irrational and their power is rational. The problem with this proof on the right-hand side is that you end the proof without actually having the pair of numbers x and y, which are irrational and raised. So all we have shown is that there exists a pair of numbers without having actually given you the pair themselves. Do you follow? Okay, so it's a classic example of a non-constructive proof. Apparently this is the constructive proof of the same thing. Oh, yeah. Whew. Okay, good. Yeah, good. Wait a second. Yeah, so okay. For example, this is Bertrand Russell's little quip on this, right? The axiom of choice, suppose you have an infinite numbers of pairs of shoes, right? You could always tell someone, hey, take always the left shoe. And that seems like a pretty clear direction of what to do, of how to pick the shoe. But if you have a pair of socks, there's no distinction between the left sock and the right sock in standard socks. And so, if you have an infinite collection of pairs of socks, the question is, are you allowed to define a function which extracts from each pair of socks just a sock? Right? In order to, if you think it's allowed to just say, hey, from this infinite collection of pairs of socks, select a sock, then you believe in the axiom of choice. Okay, people do not like the axiom of choice. Some people. And it seems to be introducing into mathematics more abstraction, less clear constructive content, and people did not think that it was true. Okay, and we're now in another sort of a problem. So you might think, oh, math's been here before, right? Didn't we have this problem with Euclid's parallel postulate where we weren't sure whether it was true or false? No. This is way worse. People did not know whether the parallel postulate was provable from axioms 1 through 4. But no one really doubted the truth of postulate 5. What we now have is a new axiom, which literally some mathematicians believe is true, obviously true, unjustifiable, by any more lower level principles, hence postulating it as an axiom, and freely ready to use it throughout mathematics. And another group of mathematicians who see the same axiom and decide that it is simply false and that it is not permissible to use this axiom. And again, no other possible point of agreement between these two groups is really imaginable, except for seeing sort of what happens if you use it in one direction or another. All right. More than really ever before, okay, you could argue that the discovery of the non-Euclidean geometries was like a crisis in the history of mathematics, and it definitely was, because now we had two independent, equally consistent but mutually contradictory branches of mathematics. But this is somehow sort of like worse. You really do have, in 1904, two groups of mathematicians out there. Some of them using the axiom of choice, and some of them just not. Whoa. Additionally, so you might think, okay, let's be more casual about this. What do you need the axiom of choice for? Well, there's this let's not even do this. There's this crazy theorem called Zorn's lemma. What is this? Yeah, let's not even do this. This is extremely abstract theorem called Zorn's lemma, which is like, never mind what it's about. It is very, very, very strange, abstract, and obscure. Turns out to be equivalent to the axiom of choice. Another famous thing, okay, but this is kind of over all of our heads, definitely my head. There's this thing called the Banach-Tarski paradox. There's an entire group of mathematicians for like 30, 40 years trying to figure out what do we need the axiom of choice for, and what happens if you assume the axiom of choice. Well, one thing that happens if you assume the axiom of choice is that you can take a ball in 3D and break it up into a finite number of sets. Okay, this is a little bit of a misrepresentation. And put it back together again to make two balls. I'm not going to say anything else about this unless someone else wants to. Good.
The sets have zero measure, which is why we need the axiom of choice.
Yeah, can you say something about that? Or not really? Okay, good.
Well, not much more than I just
There's
said.
like a
Okay,
20-minute
good.
video on this.
Yeah, this is a sort of, this is a kind of like a pop math thing that sometimes people talk about that I think most of us don't know really, including me, really what's going on. But yeah, Wilbach says that, okay, there's an entire sort of branch of math called measure theory, which sort of defines precisely like how big stuff is. And these pieces you break it into like can't be measured or something, and I don't know, moving on. Okay, blah, blah, blah. Yeah, okay, good. Here are things that require the axiom of choice to be proved, and which seem very reasonable. For any two sets, one of them is smaller than the other, less than or equal to the other. Do you feel like that's true?
Yeah.
Yeah. Give me an infinite set. Let's make it fun. Suppose both sets are infinite. And to show that one set is less than or equal to the other, we need to make an injection, right? But similar to the conversation we had, to show that given two arbitrary sets, that there exists an injection from one to the other or the other way, I need to be able to sort of pick arbitrarily an element to make the injection into. And for that, we need the axiom of choice. The very fact that every set has some ordinal associated with it is another thing that requires the axiom of choice. Even this, remember this proof that we did when we said take a union of countably many, countably infinite sets is countable?
Yeah.
Do you recall this? That proof, though I did not make a big deal about it at the time, by very, very close inspection into the details of what's going on in that proof, also requires the axiom of choice. It might actually only require the axiom of countable choice. But you will recall, how did we do that? How did we prove that an infinite number, that a countable union of countable sets was countable? Maybe I don't need to on the board. What did we do? We just wrote out all the elements in their order, right? And then we zigzagged through them. Yeah? Okay, but how do you know what order to write them in? Well, you might say, they're countable. So the fact that they're countable means that I can put them in an order, right? But what order? Right? So the very idea, so what's at issue here is, does everyone remember this proof? I don't feel like rewriting it on the board, right? We just wrote out all the elements of every set and then we zigzagged. Okay, but that's what I would call a proof, right? And to do that proof, I like constructed a injection from the naturals to all the elements of all these sets. Okay? But now if you're being more particular about things, you might say, wait. You haven't produced a construction at all. Because how am I supposed to know? Because you gave yourself sort of the power to arbitrarily decide for each of these countable sets, like what order they go in. All right, just leave it at that. All right, there are many very low-level theorems of sort of set theory and algebra and topology, which require the axiom of choice. And what is this? Oh, yeah. So what's going on here? Oh yeah, this is induction. And then we have transfinite induction, which we talked about, I think, very briefly. If you want to prove that something is true for all ordinals, you prove that's true for the zero ordinal, the successor ordinal, and then every limit ordinal. Well, using transfinite induction, we can show that, in fact, the axiom of choice, Zorn's lemma, and the well-ordering theorem are all logically equivalent to each other. And there's this famous quip about this, in which this guy says, the axiom of choice is obviously true, the well-ordering theorem, that should say theorem, obviously false, and who can tell about Zorn's lemma? So we have these three sort of theorems, which are all provably equivalent. Zorn's lemma, very strange. The well-ordering theorem, intuitively false, but the axiom of choice, at least to many mathematicians, intuitively true. All right. This is really bad. It's really bad. Many mathematicians are simply not working in this low-level set theory at all, but for those who are, it's not clear what to do with this axiom. And basically, this is a nice short presentation. And what basically happens is the entire world of working mathematicians has to, ever since then, and by the way, this is just not resolved. Like in 2018, you still must, if you are a mathematician working in a very low-level branch of abstract mathematics, dealing with these kinds of issues, you have to mention whether or not you're using the axiom of choice or not. And all of mathematics was sort of redone to figure out, okay, did I use, when I was doing this proof, the axiom of choice? If so, can I redo this proof in another way that doesn't involve the axiom of choice? What happens if I assume that the axiom of choice is false? Okay, you are free to go on the internet and read about this. If the axiom of choice is false, math gets really weird. Really weird. You get some intuitively very strange results. And now, really for the first time ever, I don't think hyperbolic geometry made this kind of schism. It was a sort of a branch, but it was a kind of a self-contained thing. Now we really have like two maths now. Okay, are you feeling your certainty, whatever you had left, falling away from you?
Lost.
Okay, it gets worse. Should we have a 10-second break, or should we just push right on to the next presentation? Woo!
Mean break.
Mean break. We should have
The mean break is, this is so dumb. Okay, we go here, we go to Hanson, and we go to... yeah, so
It's like a real pro-choice picture.
this is a pro-choice... Okay.